So welcome to everybody for joining our network technologies workshop. We have organized this workshop because we wanted to give you an overview of the work that we do in Work Package 6, Task 1. And as you know, Work Package 6 is network development, and Task 1 is for technologies. And we have three major focus areas that we are working on. One is optical time and frequency networks. The other one is quantum technologies. And the third one is our open router platform, RARE. And we will give you an overview today in three presentations. After each presentation, there will be time for questions and answers. So please, when we come to that section, please ask your questions. And also, if you have other questions, you can type it in the chat. And I expect that we will probably have some time at the end of the workshop if we run out of time for questions and answers to answer additional questions then. And if not, if we have it in the chat, we can also get in touch with you. And the session, as you know, will be recorded, and I will make it available in the events page that you also, where you also found the dial-in information and all the presentations. So let's start with our first part, which is OTFN. And I'm very happy to be able to say that we have Krzysztof Turza from PSNC, who will give the overview of this subtask. Krzysztof, please go ahead and start the presentation. Yeah, we can see it perfectly fine. Please go ahead.
Good afternoon, everyone. I present today information about time frequency distribution in fiber optics in context in European initiatives and our work in OTFN, what we're doing in the OTFN group. I start our talk from about user needs. Next, I will say a few words about time frequency service types. Next will be a little about national and international time frequency connection across the Europe. And at the last I will talk a little more about our OTFN group activity. So it wouldn't be surprising, I'm sure that it wouldn't be surprising for you, all of you, that time frequency is needed in many areas, not only in the science, but also in telecommunication, transport, navigation, power grids, and so on. But it doesn't mean that all of these areas needs the same time, the same frequency, and the same precision of the time and frequency. So every of these areas needs something different a little. Based on the Lonet DS, which I will be mentioning today quite often, this is a project which was trying to discover what is needed also across the Europe. And they were looking for user needs, what user needs. And they found that many institutions across the Europe, which you can see where are placed on the right side of this table, needs precise time and frequency. One of this group is a fundamental science institution, which so this is a pure science institutions which making an experiment and where ultra precise time and frequency are crucial for the activity. Next area is a quantum technology. Now it's very popular across the Europe, and a lot of institutions started working with this technology and exploring it. And in this area, in many cases, also time and frequency is important. So we can expect that this community will be growing, and needs in this area will be growing also. Next to Earth observation, geodesy, and astronomy, using precise time and frequency from many years, but in most cases they have to use it satellite methods to distribute such a time and frequency. In the fiber network, it's possible to achieve more precise time and frequency. So their observation and their work can be enhanced in the future if we deliver such as services to this network. The next area, positioning, navigation, synchronization, timing, especially in telecommunication, mobile telecommunication, it's rather related to some commercial users, and especially mobile connection and mobile telecommunication. The needs of precise time is growing, and this can be one of the most important commercial application of distribution time and frequency across the Europe in the future. On the left side, you can see where these institutions are placed across the Europe. So as you can see, there is a lot of places which are interested in of timed frequency transfer in Europe. So when we're talking about time and frequency distribution and time and frequency services, we have on mind at least 4 different services. The first one is relative frequency service. So we allow to comparing distant sources of frequency. This difference is a service name relative one, so we don't need to have the precise information about what this frequency is. It's a little different in absolute frequency service. This service will be needed also, especially when the SC unit of a second will be redefined. So we would have to have knowledge what exactly frequency is distributing to us. Next 2 are related to time, so relative timing service and absolute timing services. And this free first services can be using optical frequency distribution, but the last one need some dedicated distribution system for precise time transfer. So now a little about the technology. When we're talking about time frequency, this is a simple acronym, but behind that there are a few different technology and few different applications. So the first one is distribution over time and radio frequency. Radio, it's mean 10 megahertz or 100 megahertz or 5 megahertz. This is electric signals which is produced by hydrogen maser or cesium plugs such kind of devices. Such signals are converted to the optical domain, distributed across the optical distribution system to end user, and end user just only plug into the distribution system and use it without any other conversion. So it's quite easy to, from the user's perspective, to use it, such as signals. The next one is optical carrier. Here, such devices which name optical clocks producing optical frequency, which is very precise, describe light and ultra-low. It's not possible to transmit it across the telecommunication cables. We have to shift it to the telecommunication region using quite sophisticated optical frequency comps. And next is used ultra-stable lasers with dedicated cavity, and such a signals is distributed through optical fiber network to end user, which next have to convert it to the interesting frequency using frequency comp. So here this is more precise way to distribute ultra precise frequency, but it have to make some investment. It have to be make investment on the equipment here, which is quite sophisticated. So next question which we have to answer is how we can implement in our network. So this is a question if we can use dark fiber. This is the best option, but also the most expensive. Or we have to use dark channel, so some space in our DWDM system. And if it is DWDM system, this is a question if we should use C or L band solution. So if we decide on the transmission in DWDM to achieve the best possible accuracy and stability, we unfortunately have to transmit metrology signals bidirectional in a single fiber. Unfortunately, also DWDM sending signals in other way. It's unidirectional. So in forward direction DWDM system typically using one fiber, and another fiber is used for the transmission data in backward directions. In time frequency, in metrology signals, we have to use optical order multiplex in every point to have possibility to transmit it bidirectionally in the single fiber. So this is what we have to do, and this needs some modification of the transmission system. So it's in many cases it's not very easy or even acceptable by some users. If we move to national connections, we can see that there is a lot of implementation already across the Europe, for example, in CESNET, France, Italy, and Nordic countries, in Poland, and so on. So there's a lot of implementation, but unfortunately, this implementation are not using the same technology and the same systems. For example, in France, they transmit optical carriers, so optical frequency in their network, and they're using channel 44, which is a middle of a C-band. In Switzerland, they decided also to distribute in their network optical frequency service, but use channel 7, which is edge of C and L band in their network. In Czech Republic, in Poland, we're distributing both type of signals in its mean time and radio frequency and optical carrier services in our network. As you can see in here, we have different solution and different services across the Europe in each of the domain. Also, technology are different. The most common is optical carrier, optical frequency distribution system. Even that technology is well known, the implementation can be different. In most cases, people using channel 44, which is a middle on the C-band, but as you can see just before, on the slide before, also it's possible to implement in different frequency. For time frequency, we in Poland, we're using ASTAP system. This is, I think, the most advanced, the most precise system for time frequency. More popular is White Rabbit across the Europe. This is less performed, but this is well known, and many institutions decided to transmit time and radio frequency using White Rabbit devices. So if we look on the map where such a connection are implemented across the Europe, so we can see that there is a lot of such a connections, but unfortunately we have some gaps between each of them, which are not allowed now to making some experiment across multi-domain international comparison in many cases. And unfortunately, this doesn't mean that the same technology will be available in the different part of this network or this international connection. So GÉANT DS, which I mentioned before, proposed to build across the Europe multi-ring connection, international connection, which will be connecting many countries across the Europe and allow to connecting some subnets to these networks. Some subnets in national distribution network. This is idea vision of a GÉANT. So in the core network should be distributed optical carrier signal, optical frequency, plus time scale, so plus some time which is source of which have source in the UTC-K labs. To such a core can be connected some subnet networks, subnet in national networks, or the most demanding users. So this is a vision of GÉANT, how should be look like such a network across the Europe. It's mean that we will have many domains, core network or some national networks, or some connection between national networks. So it wouldn't be quite easy to make some experiments across the Europe without some international support. So in our OTFM activity, we would like to give you some help in it. And we try to build some support gateway. This will be an idea, first source of information for the NREN about time and frequency transfer, where can find some international connection, where are located some UTC and NMI labs and so on, what technology can be used and so on. And in this area, we started to gathering such information. You can find it on this link. It's still on the develop phase, so we still putting the new information. So there is a lot of missing information still, but we have, but if you find some information useful, which should be put at the, please give us information. In parallel, we building some knowledge base. This will be information about selected aspects of time frequency transfer, about technology, how to calibrate links for time transfer, how to calculate Sagnac effect, and so on, so on. So this will be another space. This is another space where you can find some useful links and some useful software and some useful information. It's also in progress in developing and putting new information there. The second hour activity is to develop an architecture which will be support multi-domain time frequency transfer and multi-domain comparison across, so comparison of a time and frequency across many different distribution network. So in our idea, we should have some front end will be communicated with end users. Some global time frequency management system will be which will be communicated with local database, and some gateways which will be doing measurement between each of the network. So in our Imagine frontend should authorize users, should give access to real-time measurement, to scheduling research and scheduling measurements across the Europe. Global time frequency service management should be responsible for gathering all information about the measurement data and status of the links. It should aggregate such a measurement and giving possibility to present it by the front end to the end users. It also be needed some communication with local database. So this local database, which will be managing information gathered from local domain, should have to be somehow structured and put in the proper way. So we would like to advise how this local database should look like. And the last are gateways, which should making measurement between two domains. and which should connecting such a domains between. And all this data or measurements which will be collected in such a gateways should be streamed to the global management system. So this is all what I wanted to tell you today. If you have any questions, please contact us on the OTFN group or directly to me or to Susanne. And if you have any questions now, I can answer. I have a few minutes to answer to you.
Thank you very much, Krzysztof, for this very interesting presentation. I don't see questions in the chat, but are there any questions from the audience? Well, this doesn't seem to be the case, but as you can all see, we have some very interesting work ahead of us. And oh, is there something?
Yeah.
Go ahead.
Yeah, so thanks, Krzysztof, for this presentation. It was very helpful and gives a nice overview of a kind of vision. I was kind of interested in, you talked about local access networks for distributing time frequency, and then which kind of makes sense, I guess, because an interconnection of NMIs is really for creating a stable reference between NMIs, a stable sort of source that has access to multiple NMIs. But then you talked about multi-domain, which in your mind is that multi-domain a multi-domain environment for interconnecting NMIs, or a multi-domain in a sort of service access, for service access?
Well, this multi-domain can be both for NMIs and end users. For example, one of the users which need common data, common scale,
Yeah.
time scale, can be all users which are related to Earth observation or fundamental science. These users not exactly need UTC scales itself, but the same scale across the Europe or across the world. It means that the observation station, which is located in Poland, Germany, and France, and Italy, should looking at the sky at the same moment and using the same reference time for the observation.
Would that not normally be solved just by all using UTC, and then if they all have an accurate UTC timestamp, does that not solve the problem? Or
well,
common?
Yes and no. Well, UTC scale itself, it's a virtual scale, and we know exactly what this UTC are after a month. Before that, there are some UTC scale implementation, local implementation, like UTC OP or UTC PL or UTC in each country is different.
Right.
And there are some difference between each of them. Unfortunately, we know about this different post-factum. It's in the post-processing of the data.
Yeah.
And using common timescales in this observation will reduce amount of the information which we have, which this institution have to correlate data from different places.
Thanks for that. So if there's time, Susanne, I'd like another follow-up question. Is that okay? I'll try and be quick because
well, we are at the end of the time, but go ahead. If it's a quick question, go ahead.
So I'm just thinking about scalability, how you make this scalable, because if there's one organization involved, it's very hard to build a network that can connect to all the European users. So in your mind, these regional networks, would they be, yeah, I think it was there, would those regional networks be NRENs or commercial partners that would provide access to local, to the national users? How does that scale?
Well, this is, I think we should do take more consideration in the GÉANT community to help this international communication between different distance users across located in different countries. I heard also from colleagues they want to cooperate with somebody from CERN and using the same signals in Poland and Switzerland, and this is mean that we somehow help them. And this is this idea of service which will be connecting these users and providing measurement data.
Yeah.
I think it's crucial to implement in the future.
Okay.
And we proposing as a OTFN group, proposing some architecture of such a system, but we expect that in the next years we will be able to prepare such a service operational or implement such a program for connecting multi-domain.
I think that's going to be the interesting challenge for the community. Okay, so yeah, thanks for answering those questions.
Thank you very much for these interesting questions.
Yes, thank you very much to Krzysztof again. And I'm sure by now all of you are very jealous of the exciting work that we do in Task 1. But just wait and hold on, because we have much more to come. The next topic is quantum technology, and Piotr Rydlichowski from PSNC will present. If you have other questions for OTFN, please put them in the chat or contact us. Piotr?
Yes,
please go ahead. I know you have also something very interesting for us in store.
Yeah, thank you. I think you should see.
Yes, we can perfectly.
Yeah, my presentation. So thank you, Susanne, for the kind presentation, introduction. So I will move to the topics connected with the quantum key distribution. I hope it will be not boring, because I will talk about a lot of documents. So I hope that it will be interesting. But anyway, all the documents that I will mention in the presentation, it would be accessible on our wiki, so you can go to them and refer, because we simply have we're out of time to process all the documents during the presentation. But anyway, so I would like to discuss a little bit about the standardization landscape for the quantum key distribution, and in general quantum communication and the quantum networks, because these topics are of course connected. We can see that the QKD can be a first step, and it will be an evolution to the general quantum communication. It will be a process of evolution of the existing QKD technologies toward the general quantum communication. We can assume that the QKD will be a first practical use case that, let's see if it will be widely adopted and implemented. So why standardization? Maybe I will give at the beginning 3 reasons why we should focus on the standardization in terms of the QKD area. And in my view, there are three reasons. First of them is simply security. If we want to have our solutions that are connected with any security technologies, we need to have a certification and standardization for these solutions, because no one will use it, will not guarantee that in the way it's compliant with the requirements. So this is the one reason. The second reason is the complexity. So if we want to build a market for the quantum technologies and the QKD solutions, we need to allow the smaller companies, startups, to take an easier approach toward the system specification. For them, it's very, very difficult to work on the technology from the scratch. So if they need to work on all the elements at the same time, which are currently under certification, it's simply not possible for them. So that's why from their side, it's very optimistic to have standardization, because it will help them to focus on the other areas in terms of the QKD systems development. And the third reason is, as I mentioned, it's connected with the quantum communication in general. So the baseline and the ground and the foundations that we built here will be used also for general quantum communications. So those are the three main reasons. So now, who is doing the standardization? So actually, we can divide it into three groups. So the first one was ETSI back in 2008, which started an industry specification group for quantum key distribution, ISG-QKD. And they focus on the protocol security, implementation security, component and module characterization, key delivery and use cases. So all of these elements are under interest of this group. And up to the moment, they have several reports, documents that I will mention in the presentation, 14, and it's still, of course, pending. And it's a great input for a lot of different projects. On the other side, we have also other standardization organizations such as CEN-CENELEC, ICO, IEC, IEEE, and IETUT. They are connected with Europe and also worldwide reach, so independently. And because of the large interest in the quantum technologies, a lot of new members joined the group, standardization groups, and they really put an effort and input to all the documents. And it's very interesting discussion between them during the document preparation, and it's really an important point at the moment. So in terms of the reach of the standardization, we have to divide it in the, I divided those elements in three categories. So the first category, the lowest, is the national standardization. And some countries already work on the national level regarding the implementations and standardization of these technologies. One of the examples here are the examples. So BSI in Germany, cryptographic methods recommendation, GÉANT, a report. There is NIST cryptographic technology group in US that is taking care of these technologies also, and CrypTrack also in Japan, the Cryptographic Research and Evaluation Committee. So these are the examples on the national levels. Then we have the European level of the standardization, and here we have the CEN-CENELEC Focus Group on Quantum Technologies, FGQT, ETSI group, ISG-QKD group that I mentioned previously, and also ETSI-TC Cyber Working Group, QSC9, Technical Committee for General Cybersecurity and Quantum Safe Cryptography. And on the international level, we have several, I would say, implementations and organizations. So one of them is ISO-IEC, and with the JTC1SC 2712 group, they actually a subcommittee, they have a working group 3, which is working on security evaluation, testing, and specifications of these technologies. And they actually, at the moment, they have two, they perform two security evaluations reports under this group, and both are regarding with connected with the applications of the QKD technology. From the ITUT side, we also have a group which is in generally working on the future networks and next generation networks. And a part of that is the QKD technology. And you can identify those documents with Y prefix. And they tackle similar elements as I mentioned for the ETSI ISG group. And also we have a quantum internet research group, which is part of IETF, that is drafting some proposed reports, documents regarding general quantum communication and networks. We have Crypto Forum Research Group, international group by IEEE, Quantum Com, software-defined quantum communication, and the group which is associated with the mobile providers, GSMA Internet Group. They are focused on the general cybersecurity aspects of the systems. So this is the reach and the players, I would say. And now the documents, a brief overview of the documents. So in terms of the quantum communication module security, so the module level for the quantum key distribution, we already have several documents, and they focus on the internal interfaces, threat assessment, security proofs, QKD module security specification, component characterization, characterizing optical components performance, communicate device and communication channel parameters for QKD deployment, and the very important document protection profile. Why it's important? Because it's the protection profile, it's a baseline for preparing certification documentation for given device. So you tackle all the issues connected with life cycle of the security equipment, how it should be tested, how it should be certified. So all the baseline in this document, it is a 100 pages document. I recommend to at least have a look at it, because it defines how, from the operational point of view, those devices are looked at the moment. So this is what you already have, and what is currently being drafted is the update to the security proofs, implementation security against Trojan horse attacks in one-way QKD systems, how to characterize the optical output signals of the QKD transmitters. The updated protection profile document was just published this month. Design of QKD interfaces with authentication, security requirements, test and evaluation methods for quantum QKD distribution. And this is two-part document from ISO-IEC. So we have here ETSI and ISO-IEC. So it is in terms of the modules, and in terms of the network interoperability, we also have a number of documents with the general low-level application interface to the QKD systems, GS QKD 004, and very known QKD 014, which is a REST-based protocol with the access to the QKD systems and the keys. And the two new documents, 0.15, A18, which are focused on the software development, software-defined approach to the QKD systems and how they should be managed and accessed. So the documents are published, and the documents which are under preparation is QKD 020, which is important document in terms of the interoperability of QKD systems. And the same for ITUT, a series of documents which specify different interfaces for the quantum key distribution networks. So the quantum key distribution and network framework. So these documents are related with the network interoperability, and the other documents here that are being that are already published are from the ITU also, group 13, overview of networks supporting quantum key distribution, functional requirements, architecture, key management, control and management, software-defined networking control, requirement for quality of service parameters, framework, architecture for quality of service assurance, and machine learning-based quality of service assurance, are also interesting documents. These are published, and in terms of the documents that are being drafted at the moment, also from ETSI, ITUT, and from both ITUT groups. Architectures, actually an update to the document, and functional requirements, also update to the functional requirements, architecture for machine learning enablement, QKD internetworking, functional architecture enhancement for machine learning based quality of service assurance, measurement methodology for quality of service parameters, quantum key distribution network interlocking architecture, model for automating management and control, federation access, internetworking, and for software-defined networking control, and framework for QKD network resilience. So all these are connected with interoperability. And now the last group, the standards that are connected with the roadmaps, applications, and the use cases. So here the documents that we already have are from CEN-CENELEC, ETSI, and ITUTs, group 13. These are the simply roadmaps for the standardization, use cases, specification, integration of quantum key distribution network for secure storage network, deployments, applications of machine learning. And the documents that are being prepared at the moment from ITUT, functional architecture for integration and secure storage network, and update, actually update to the existing documents regarding the use cases, and what is interesting, that beyond also the QKD network, QKD networks, but also to general quantum communication networks. So this is use cases, and in terms of the standards in quantum network security, what we already have is from ETSI and ITUT, group 17, quantum safe cryptography, case studies, deployment scenarios, distribution networks, key management, key supply for the QKD networks. Also, in all the elements connected with storage, security considerations, and hybrid approaches for key exchange, with quantum key distribution, so the regular algorithms, and also possibly post-quantum. And what is prepared, draft at the moment, is from the ITU group 17, actually also updates to the existing documents, so authentication, authorization, security requirements for measurements, for measures for quantum key distribution networks, control and management, security requirement design for quantum key distribution networks, trusted node. It's also important document because we know that we will need a trusted nodes because we will not be able to reach the QKD transmission in one hop between the end users. And now the other standards that are currently that are already published or being prepared is the algorithmic framework, computing applied, limits to quantum computing applied to symmetric key sizes, quantum safe key exchanges, so the new algorithm, cyber quantum key distribution, simple vocabulary. This is what we have. And what we need to, what is actually being updated right now or drafted new is updated document regarding the vocabulary, new software-defined networking approach from, and here from IEEE, standards for quantum technologies definitions, post-quantum recommended practice for post-quantum cryptography migration, which is also very important element, how to migrate to new solutions, and the standards for post-quantum network security. And also from IRTF, from Quantum Internet Research Group to documents, architectural principles for quantum internet and application scenarios for the quantum internet. And now, I think from the documents that I mentioned, that I presented, I think we can get the general idea what is being drafted, what is being prepared at the moment, and what is missing. So what is missing? So we see that there is a lack of addressing in terms of the new QKD protocols. So the existing QKD protocols are under specification, but the new protocols not yet. We need to describe also the new components, which are, for example, the new integrated photonic modules for QKD modules. Apologies. Gaps related to the performance of the QKD networks, the way the key are delivered, gaps regarding the control network and management, the interfaces, and very important, the vocabulary. So we still don't know how to properly use and how to in uniform way use the conventions and the names for different modules and processes. The network security from the QKD networks, and in general, I would say the integration of the QKD generated keys to the higher levels for the applications and services. So these elements need to be addressed and currently are being addressed in the draft documents. And we know that with this slide, I would like to show the 5 very important, I would say crucial strategic elements that needs to be addressed in terms of the standardization. So in general, the quantum communication module and its link security, how to use the elements on the interoperable fiber network, how to secure the quantum network, how to address the free space QKD, both in the terrestrial and satellite solutions, and the quantum technologies and quantum key distributions. We know they are crucial development elements in terms of the standardization, but they need to be coordinated between each other, so together. Yeah. So these are two elements. Those are elements that I want to show. Please free to ask questions. I will try to ask them. I will try to answer them. And if you wish to address and check the documents, yeah, I will on the wiki of the group of the work package will include the access, the specification of the documents, and you can try to check them some of them are openly available and some of them unfortunately not. Yeah, so thank you.
Thank you very much, Piotr, for such an extensive overview of these documents. We have one comment by Tim in the chat about the recent publication of RFC 9340 and also
Yes.
a link to the use cases.
Yeah, sorry,
Yeah.
Piotr, it's you've got a huge list of documents there. That was only published last month, so it's not surprising you might have just missed that, but it's good that it's been finally published.
Yes,
Piotr didn't mention it probably because it's there's a link on our wiki already for it.
Okay, it was mentioned as being under approval on your slides, that's all, sorry. But yeah, it's a good document, and the use cases is a very interesting document to read.
Yeah, thanks, Tim. And in general, we are also working together with colleagues from the OpenQKD to finalize the whole updated document regarding the standardization, and all of these new elements and the challenges and problems will be described there. And the document is in the final form, so I hope it will be published very soon on the European Commission website. Yeah.
Great.
Yeah, thank you very much. I mean, this is this seems very complicated, and I guess between the organizations that you mentioned, which are basically from the Western world, it's basically there's a lot of collaboration. But what about China or other countries? And couldn't there be some kind of a conflict of the different standards come up and there's no collaboration, or maybe little? I don't know.
Yeah. So indeed, there is the issue that too many, well, maybe not too many, but many partners are working on the more or less the same topics. So now the challenge is to try to, let's say, find a common approach to these problems and reduce the burden for this work. Yeah, exactly. This is one of the challenges. And in terms of the other countries, of course, China is drafting its own standards, and in many areas, we already know that it will not be compatible. They took a completely different approach, and it will be a different implementation, different solutions. So simply a different technology from their point of view.
Okay, I see.
Yeah. The China is already working on its own standards. Yeah. Some of these elements probably will be more or less the same, but in many areas they took a completely different approach.
Yes. Well, thank you. Any other questions or comments? Well, this doesn't seem to be the case. If you do have a question, you can still put it in the chat for later. So thanks again, Piotr. This is overwhelming, all these documents, and thank you for trying to sort things out for us and giving us such a detailed overview.
Yeah, thank you.
So now let's go to the third session, which is also very exciting. It is on RARE, our router for academia, research, and education, and Simon Leinen will present for us from Switch. Simon, please share the screen. Perfect, looks perfect.
Okay, the right one.
Yes.
Hello, welcome, thanks for listening. So I'll talk, as Susanne said, about the RARE part of WP6T1. The slides I mostly got from Frederic, who is the technical lead for our activity, but who couldn't be here to present it himself because he took a bit of vacation. So brief look at the agenda. We talk a bit about the activities in GÉANT 5.1. This is a follow-on of years of activities in GÉANT 4.3. Talk a bit about how we released the software, a new initiative to publish validated designs, Also the global testing infrastructure we call the GP4L with some intentional ambiguity here as to what the G stands for. Then about network management and community support. And I hope we have some time for discussions. Unfortunately, I didn't check the timing yet. So rare and free router, for those who don't know this, it's the router for academic and research environments. It's an open source routing platform that we use to create a network operating system that runs on commodity hardware such as white box switches and also white box Intel hardware. We see some options later. Free router is a pre-existing piece of software that implements a wide variety, really wide variety of control plane protocols in routing and MPLS and so on in Java. That was written by Csaba Máté as part of the Hungarian NREN. So the combination of the two, we usually talk about rare/free router. And there's a pointer for those of you who want to know more. So as I said, the common control plane for all rare implementations is free router. And principally, we could think about using something else, but that has done a good job for us over the years. And the rare project added a few adapters to high performance data planes. One set is based on the P4 language. So it's a protocol independent programmable packet processors or something. It's a some people might have remembered that this was touted as sort of the OpenFlow 2.0 or successor of OpenFlow. It's much more flexible than OpenFlow, for those who know that. That can be used in an emulator, which is the left option we have here. But interestingly, there's also a high performance and low cost hardware implementation that talks P4. That was done by a startup called Barefoot, which was later acquired by Intel. And this turned out to pose some problems I will talk about later. There are other hardware implementations that support P4. For example, Cisco's latest Silicon One chips also do, but it's not clear whether this could also be amenable to a rare target. And another interesting data plane implementation that we support is DPDK. So it's again an Intel product. It's a high performance data plane, user space data plane for Intel-based or AMD-based boxes. It also has its uses. So in GÉANT 5.1, we want to mainly focus on community requirements and work with some concrete potential rare users who may demand new features to be implemented, but with a clear view on solving particular problems. Also, we want to make these solutions reproducible in that we provide not just running code, but also like sample configurations and documentation so that people can just use that as a toolkit without having to study too much, which is currently the hurdle is a bit high for some applications. We also work on documentation and making this available on docs.freerouter.org. Over time, there's already quite a few nice examples there, in particular in the form of these rare free router validated designs that I will go into a bit more deeply later. Another focus is the developer community, because as I said, free router was mainly the product of a single person over many years of intensive work, Csaba Máté, who's still continuing to develop this, but it will be nice to have other developers be able to contribute effectively and get them onboarded to the project. That's another goal we have for the coming years. And the basic objective is to increase the uptake and the trust in the solutions provided by Rare Free Router, in particular in our NREN community, but also beyond. We'll see a few examples. So as for feature development, we have some activities in protocols. For example, the Rift is a modern approach at building very large-scale data center fabrics using layer 3 routing, which has been recently proposed in the IETF. And Free Router has one of the first implementations of these, and I hope we will be able to do some interoperability testing there, maybe at the IETF hackathon in November. Another recent improvement was that we can now compress the FIB, so the hardware forwarding table, so that we fit a fairly large number of routes, even in this very high-speed routing silicon. We can use the Tofino chips, which unfortunately have quite limited table space. There's also some efforts of virtualizing a Rare and Free Router so that you can run it easily in experimental settings, and to instrument the system so that we can look in detail at counters such as buffer occupancy, and export them to other systems. And we're also looking for new ideas. And on the front of targets, we currently support the 2 existing versions of the Tofino chip, one that has something like 6.4 terabit per second system capacity, so you can build like 64 times 100 gig port or 32 times 100 gig port switches, as well as the next generation Tofino 2, which doubles the capacity. There was also supposed to be a Tofino 3, a subsequent generation that would again have doubled that, but unfortunately Intel decided to discontinue development of the Tofino platform that they had acquired a few years ago. So we are in talks currently with Broadcom, another and the very dominant vendor of switching ASICs, and hopefully we'll be able to implement Rare also for targets from that vendor, which is very, very relevant because they're very widespread in the industry. And we also intend to support some DPUs. So those are like network accelerators that can be used in switches or servers. We'll talk about an example soon. So some of these validated designs we are now working on and documenting. Again, Free Router is very versatile and implements a wide range of protocols that can be used in many use cases. And we're trying to document that in a usable fashion by going into specific use cases and giving workable examples of implementations and specific tasks such as doing upgrades. One such example is a regional network in northern France, GÉANT, that wants to build like a metro ring containing sites in 3 towns. I think it's Rouen, Le Havre, and sorry, I forgot what CFR was. That is something that is being designed by our French colleagues from the regional network. So this started out by being like a normal routed ring network. Then it was discovered that Free Router also acts nicely as a route reflector, and it has a very high performance BGP implementation. And it could also be used in an exchange point, like one that is existing in the region as the Normandix. So it can cover quite a wide range of use cases that appear in, for example, a regional network in a large region of a large country. And there are many applications that we're still looking at in the areas of DDoS mitigation, for example, detection and mitigation, controlling wireless infrastructure, SOHO and broadband gateway situations where FreeRouter has also already been used in other places, and also in 5G, the user, UPF function. And there are people actively working on this in GÉANT 5.1 right now. So another example, we recently had received a note of interest from colleagues at Juniper who had been implementing a proposal of theirs to extend BGP to communicate different transport classes. That is something that could find uses also in 5G, namely an interconnection of different 5G networks, where each 5G network supports slicing. It's one of the new headline features of 5G. And that would, this BGP extension could be used to extend the slicing across provider boundaries. And actually there are two competing proposals right now being discussed in this IETF interdomain routing, IDR working group. One of them is BGP-CT, class for transport planes. The other is called BGP-CAR. Forgot what that meant. And so Juniper was behind one of these proposals, and they were very interested in demonstrating that they were actually, they had achieved interoperability between two different implementations, and discovered that FreeRouter had implemented this protocol, very recent protocol extensions. So they convinced us to go to a large interop event that happens every year for many years, decades in Berlin, where we went in March to set up interoperability tests. It was a very impressive event where all large router vendors participate traditionally, and a few smaller ones. And now this, I think we were the first like open source project, so that had to accommodate some peculiarities, but we managed to demonstrate that we were interoperable, and now Juniper is using this as an argument in the discussion of the standards. So this shows that our work has some impact even in the broader industry beyond NRAMs. It was completely unplanned, but I hope we will find more examples of that in the future. So for talking about hardware, there are some SOHO, like for small sites, branch offices, and so on, or smaller schools, applications where a high-speed router with 100 gig interfaces is overkill, but you can run FreeRouter and RARE on small appliance like Intel boxes, which cost not a lot, and will work just the same, support all the features and MPLS fanciness that you usually don't get with such small boxes. For the Tofino hardware, one example that we've used successfully is the EdgeCore Wedge, which is something I think was designed for Facebook years ago, and it is available very easily and cheaply on the market, and it has 32 100 gig ports. So it's very powerful and comparable to very expensive routers, with some caveats, for example, that the routing tables and also the buffers are limited. So you can't run the full routing table, and you must be careful when you like mix interface speeds that you could have problems with small buffers. But otherwise, it has this very rich feature set also. And most of the features are implemented at line rate, thanks to the P4 programmability. There are actually quite a few variants of these Tofino switches, which always surprises me. One of them is by Stordis, a European company who have like variants of the interfaces, has some 100 gig interfaces and a bunch of 10 or 25 gig interfaces, as well as low speed 1 gig interfaces, which requires some additional hardware that we had to add support for. So it's every time we support a new kind of box, there's a lot of work has to go into that, but we have been quite successful in that. I think we probably support the widest variety of these Tofino boxes, and this has also driven some uptake that we'll see later in the GP4 lab. A new example is a Chinese company called Aster Fusion, who builds a Tofino switch, which has additionally these DPU boards in there, one or two. I think the ones we got, I'm not sure whether they have one or both equipped actually. And on these DPU boards, there's an ARM-based DPU, but it's really ARM cores, a lot of ARM cores that allow you to do like what you call deep packet processing that the very high-speed Tofino is not capable of. But when you do like content, whatever analysis for security applications or whatever, these can be very handy. They only run at like 1 or 2 times 100 gig, don't have as much bandwidth as the P4 chip, the Tofino chip, but they have a lot of processing power that you can use for deeper analysis. So we have the box basically running, but it's still a lot of work getting useful functionality out of these DPUs. In principle, FreeRouter is positioned very well for this because it already supports distributed data planes, so that one control plane can control a data plane that runs partly, for example, on the Tofino switch and partly on something else, such as these DPUs. So it's something we look forward to, but it's also still a lot of work. So let's talk a little bit about the software lifecycle and how we release it. We package the software, which in the case of a Tofino switch consists of FreeRouter, the underlying OS, and importantly, the Intel or Barefoot SDK, parts of which we have to ship so that we can control the switching ASIC. And this NICs-based packaging now allows for very convenient installation and upgrade processes. So we're getting much closer to the goal that our product should look like what people are used to when they have been working with Cisco or Juniper. Also, there's extensive testing run as part of the release process. And we hope that we will add some performance testing as part of the project. And also recently we have added support to Container Lab, which is an example of a platform that allows you to run virtualized routing OSs for tests and others. And since I think 1 or 2 weeks ago, RARE is officially supported as part of the Container Lab distribution, which makes it even more accessible for people who want to play around and test extensive topologies with RARE and other systems. So another thing that is related is actually part of work package 6.2, strictly speaking, is the global P4 lab, which we used to call it GÉANT P4 lab, but it has grown beyond the GÉANT footprint, as you see here, by adding a bunch of nodes now in North America, also in South America, in Brazil in particular, and in South Korea. And I think one driver was that people bought these very cheap Tofino boxes and found that it was very hard to find usable software. And then they discovered RARE, which installs easily and does useful things. So I think in this way, we got quite a few people interested in this. And the map you see here is the status of last December as of the supercomputing conference where Frederick gave a presentation. But in the meantime, it is already growing. So we now have also equipment in Tokyo. Briefly, because I'm running out of time, we also, with this growing infrastructure, we face the problem of monitoring the infrastructure, and what we're doing is we're using NMAS for this with good success. So we have instance slice of this other GÉANT service that allows to deploy monitoring tools and other management tools very easily. So RARE and GP4 Lab, GP4L has become a showcase also for this other product. Yes, and we're looking forward to more interesting work and also exciting, surprising work. I think Friedrich made contact recently when he presented at the APAN conference in Kathmandu. So there seems to be some interest in building networking up on the slopes of Mount Everest. So maybe in a few months, we'll have some rare free router boxes running at 5,000 meter altitude, who knows? Anyway, thanks for your attention, and I hope we'll have some questions. Otherwise, I leave some pointers here.
Thank you very much, Simon, for presenting this impressive work. Yes, it's really nice how this user community takes off, and I hope we can expand it and also continue the interoperability tests and just keep working on these different use cases. Other questions? There's one comment in the chat from Tim. It is a pointer to an event that takes place later this afternoon and is related on network programmability, the road ahead.
Yeah, that's a very good pointer. It's the P4 workshop has been taking place earlier this week. And I haven't been able to participate. It's also on site somewhere in California. And I hope to hear some news about, maybe not good news, about where the industry is going with P4. Because, as I said, Intel has discontinued or is discontinuing development of the Tofino chip, which was like the exciting implementation of P4, and that we were able to use with a very good success in RARE and also in some other NRAN applications. So that really leaves a gaping void, and it seems to be that the attention in the P4 community seems to be moving to this DPU space, so accelerators for example, in the server side on cloud applications. It's something that people have been looking at. It's also interesting in terms of scale, but I hope there's also something that is usable for us core networkers. So thanks for the pointer, Tim.
Thank you very much. Any other comments or questions? If that's not the case, then if you did enjoy the presentations we had and our work, let me point you to some other activities and events that are coming up, where you can follow the work we do in Work Package 6. Can you see the screen? I think you should be able to.
Yes.
Thank you. We have upcoming events where we will be on site. The next one, May 8th to 11th, will be at the TechX in Atlanta, Georgia, with a presentation on orchestrating service automation. We will also be at the 18th SIGNOC in Stockholm, May 16th and 17th, presenting Argus and Personar. And the next virtual event will be NetDev Platforms, and you will hear more about NMAS, SPA, and the Global P4 Lab. This will be May 23rd, and you can already register for the event. And we have a Quantum Solutions event on June 21st, where we will invite several vendors to provide an overview of products and quantum solutions. And of course, we will also be at the TNC in Tirana, and we will have presentations in several sessions. For example, Ivana will be doing the session for the GNAG community meeting. And there will also be a session on global packet delivery that works. We will have several lightning talks in part 1 and part 2 on Argus, on QKD distribution in the GÉANT network, and on Wi-Fi monitoring. And we will have a presentation in the session, Robots Rule the World, from sitting to energizing, where do you want to be? This is on OAB. And we will have a quantum session on June 8th. You find all these links and all the presentations that we heard today, and also the recording will be part of the event page. You can already find the presentations, and I will add the recording as soon as it's available. Please send us your questions or your comments, and we look forward to seeing you in our next InfoShare. So thank you all, and hope to see you soon again.